In a remarkable turn of events, scientists at CERN, the European Organization for Nuclear Research, have unveiled a discovery so profound that it defies the established principles of modern physics. This revelation comes after years of experimentation and analysis, and while the specifics remain under careful study, what has been made public hints at a paradigm shift in our understanding of the universe. The discovery, cloaked in mystery and intrigue, is causing ripples across the scientific community as experts grapple with the implications of what some are calling the impossible finding. Before we start, hit the like and subscribe buttons for more exclusive news. At the heart of this groundbreaking revelation is an anomaly observed during one of the many high-energy experiments conducted at the Large Hadron Collider, LHC. The LHC, the world's largest and most powerful particle accelerator, has long been a beacon of cutting-edge physics, a place where scientists probe the smallest building blocks of the universe. For years, researchers have been hunting for new particles and forces that might help explain the mysteries of dark matter, dark energy, and the unification of forces. Yet, this particular discovery was something no one anticipated. The CERN scientists stumbled upon the anomaly while examining data from collisions involving protons at previously unprecedented energy levels. What they observed did not conform to the standard model of particle physics, the framework that for decades has explained the behavior of known particles and forces with remarkable accuracy. Instead, the data suggested the existence of a phenomenon that appeared to operate outside of these established rules. It was as though the universe, in that fleeting moment, had revealed a hidden layer of reality, one that had remained elusive to even the most brilliant minds of our time. Initially, the scientists were cautious. They knew the enormity of what they were observing and understood that extraordinary claims require extraordinary evidence. They ran simulations, analyzed the data from every conceivable angle, and sought to eliminate the possibility of error or misinterpretation. Yet after months of scrutiny, the evidence persisted. This was not a statistical fluke, nor a malfunction of the LHC. Something new and wholly unanticipated had emerged from the chaos of colliding particles. The impossible was real. The implications of this discovery are staggering. For one, it suggests that the standard model, while immensely successful, is incomplete. Much like how Einstein's theory of relativity revolutionized classical physics, this new discovery hints at the need for a more comprehensive framework, one that can account for forces and phenomena that the standard model cannot explain. It opens up a Pandora's box of questions. Could this be a clue to the nature of dark matter, that elusive substance that makes up most of the universe's mass but has yet to be directly observed? Or does it point to a deeper, more fundamental layer of reality, perhaps tied to quantum gravity or even the multiverse? The discovery also raises tantalizing possibilities about the nature of time and space themselves. Some physicists have speculated that this anomaly might be evidence of dimensions beyond the familiar three of space and one of time. These extra dimensions, if they exist, could radically alter our understanding of the cosmos, potentially offering explanations for phenomena that have long baffled scientists. It's possible that we are on the verge of uncovering a more complex and rich structure of the universe, one where the fabric of reality is far more intricate than we ever imagined. One of the most exciting aspects of this discovery is its potential to bridge the gap between quantum mechanics and general relativity. For decades, these two pillars of modern physics have existed in a state of uneasy coexistence, each providing a powerful description of reality but in vastly different realms. Quantum mechanics excels at explaining the behavior of subatomic particles, while general relativity describes the large-scale structure of spacetime. However, these two theories have proven difficult to reconcile, and physicists have long searched for a theory of quantum gravity that could unify them. The anomaly observed at CERN might be a step in that direction, offering new insights into how these two frameworks might be connected. The discovery also has profound implications for the search for a grand unified theory, a long-sought goal of theoretical physics that aims to unify the three fundamental forces of the standard model, electromagnetism, the weak nuclear force, and the strong nuclear force, into a single framework. While the anomaly does not provide a direct solution to this problem, it suggests that there may be new forces or particles at play, ones that could lead to breakthroughs in our understanding of the fundamental forces of nature. As with any major scientific discovery, this one raises as many questions as it answers. What is the nature of the new phenomenon? Is it a new particle, a new force, or something entirely different? How does it fit into the broader picture of the universe? And what, if any, practical applications might arise from this discovery? While it's too early to provide definitive answers to these questions, the possibilities are tantalizing. The discovery could open the door to new technologies, perhaps even leading to advances in fields as diverse as energy generation, materials science, and space travel. In the world of theoretical physics, some of the most exciting ideas being explored in light of this discovery revolve around the concept of symmetry breaking. Symmetry plays a crucial role in modern physics, governing the behavior of particles and forces at a fundamental level. However, when symmetry is broken, it can lead to new phenomena, such as the emergence of mass in the Higgs mechanism. The anomaly observed at CERN could be an indication of a new form of symmetry breaking, one that reveals previously hidden aspects of the universe's structure. Another intriguing possibility is that the discovery could offer insights into the nature of quantum entanglement, a phenomenon that Albert Einstein famously referred to as spooky action at a distance. In quantum entanglement, particles that are separated by vast distances can still instantaneously affect each other's states, a phenomenon that has puzzled scientists for decades. Some researchers have speculated that the CERN anomaly could provide a new window into the mechanisms behind entanglement, potentially leading to breakthroughs in quantum computing and information theory. The excitement surrounding this discovery is palpable, not just within the scientific community, but also among the general public. For years, the mysteries of the universe have captivated the human imagination, from the birth of stars to the nature of black holes. Now, with this new discovery, we are closer than ever to unraveling some of the deepest mysteries of existence. The questions it raises touch on some of the most fundamental aspects of reality. What is the nature of space and time? How do the forces of the universe interact? And what, ultimately, is the nature of existence itself? Even as the scientific community rushes to understand the implications of this discovery, there is a sense of wonder and awe at the sheer magnitude of what has been uncovered. For generations, humans have sought to understand the universe, from the early astronomers who charted the stars to the physicists who developed quantum theory and relativity. Yet, with each new discovery we are reminded of how little we truly know. The universe is vast, mysterious, and full of surprises, and this latest revelation is a testament to the boundless potential of human curiosity and ingenuity. As research continues, the world watches with bated breath, awaiting further details and clarification. For now, one thing is certain: the discovery at CERN has opened a new chapter in our understanding of the cosmos. It has shattered preconceptions, challenged established theories, and hinted at a reality that is far more complex and strange than we ever imagined. The implications of this discovery will likely reverberate for years to come, shaping the future of physics and transforming our understanding of the universe in ways we cannot yet fully comprehend. In many ways, this discovery is a reminder of the beauty of science, the idea that no matter how much we think we know, there is always more to learn, more to explore, and more to discover. The universe is a puzzle, and with each new piece that we uncover, the picture becomes a little clearer, even as new mysteries emerge. The excitement generated by this finding serves as a testament to the enduring spirit of exploration that drives scientists forward, even in the face of the unknown. The CERN scientists may have broken their silence, but the questions raised by their discovery are just beginning to speak to us. As new theories are proposed and experiments conducted, we will undoubtedly learn more about this strange anomaly, and perhaps, in time, we will come to understand the deeper truths it holds. For now, however, the discovery stands as a beacon of scientific progress, a symbol of humanity's unrelenting quest to understand the universe and our place within it. The impossible, it seems, has become possible, and the implications are nothing short of world-changing. The full implications of CERN's discovery are still being unraveled, and the consequences could stretch far beyond the realms of physics. This breakthrough forces us to reconsider the very nature of reality and challenges the fundamental frameworks that have guided scientific inquiry for centuries. As scientists dive deeper into understanding this mysterious anomaly, many are beginning to speculate on how the discovery could reshape not only our understanding of the physical universe but also the future of technology, human cognition, and even philosophy. One of the most immediate areas of inquiry revolves around how this new phenomenon interacts with our current knowledge of quantum mechanics. Quantum mechanics, often regarded as one of the most successful theories in scientific history, has long governed the behavior of subatomic particles and described the probabilistic nature of the universe. It's a theory that has led to extraordinary advancements, from the development of semiconductors and lasers to the burgeoning field of quantum computing. But while quantum mechanics has enjoyed tremendous success, it has always harbored mysteries that even the greatest minds have yet to fully explain. Could this discovery at CERN finally offer a key to those mysteries? Some scientists believe that it may provide insights into quantum phenomena that were previously thought to be beyond reach. For instance, the notorious wave-particle duality, which describes how particles such as electrons exhibit both wave-like and particle-like behavior depending on how they are observed, has long defied complete understanding. The anomaly could shed new light on how particles behave at the quantum level, potentially offering a more coherent explanation for the bizarre behaviors observed in the subatomic world. The discovery may also offer new insights into the phenomenon of quantum superposition, in which particles can exist in multiple states simultaneously until measured or observed. The mysterious collapse of these superpositions when observed, a fundamental part of the famous Schrödinger's cat thought experiment, has long puzzled physicists. Theoretical interpretations such as the many-worlds theory suggest that each time a quantum event occurs, the universe splits into multiple parallel realities, each corresponding to a different possible outcome. If the CERN discovery hints at the existence of hidden dimensions or parallel universes, it may provide experimental evidence to support such bold ideas. This would, in turn, shake the foundations of our understanding of time, space, and the nature of reality itself. Another tantalizing aspect of this discovery is the potential impact it could have on the development of quantum technologies. Quantum computers, in particular, stand to benefit from any new understanding of the quantum realm. These devices, still in their infancy, rely on principles of superposition and entanglement to perform calculations at speeds far beyond those of classical computers. If the discovery at CERN reveals previously unknown quantum effects, it could pave the way for a new generation of quantum computing technologies that would dwarf the capabilities of anything that exists today. This could lead to breakthroughs in cryptography, artificial intelligence, and data processing that would transform industries and revolutionize modern life. Beyond quantum technologies, the implications of the discovery may extend to the development of new materials with extraordinary properties. Advances in material science have often followed in the wake of discoveries in fundamental physics. For example, the discovery of graphene, a two-dimensional material with remarkable strength and electrical conductivity, was made possible by understanding the behavior of electrons in crystalline lattices. Similarly, the CERN anomaly could point to new materials that harness unknown quantum effects or operate under previously unobserved forces. These materials could be stronger, lighter, and more efficient than anything we currently have, with applications in everything from aerospace to electronics. Some researchers have even suggested that this discovery could unlock the door to advanced forms of energy generation. For decades, scientists have sought to harness the power of nuclear fusion, the process that powers the sun and holds the promise of providing virtually limitless energy with minimal environmental impact. While significant progress has been made, achieving controlled fusion has proven extraordinarily difficult. If the CERN discovery hints at new fundamental forces or interactions between particles, it could potentially offer new pathways to achieving nuclear fusion or other forms of advanced energy generation. Such a breakthrough would have profound implications for addressing the global energy crisis, reducing our reliance on fossil fuels and combating climate change. Perhaps even more speculative, but no less exciting, are the potential implications of the CERN discovery for space travel and exploration. The anomaly observed at CERN may suggest the existence of new forces or dimensions that could radically alter our understanding of how space and time operate. If scientists are able to harness these forces, it could lead to the development of propulsion systems that operate on principles far beyond our current capabilities. Theories of warp drives and faster-than-light travel, long relegated to the realm of science fiction, might move closer to reality. Such technology could allow humanity to explore distant star systems and galaxies, expanding the horizons of our civilization in ways that are difficult to even imagine. In addition to its impact on science and technology, the discovery could have profound philosophical implications. For centuries, scientists and philosophers have grappled with questions about the nature of reality, consciousness, and the universe's place in the broader cosmic order. The new phenomenon observed at CERN challenges the very foundations of materialism, the idea that the universe is composed of matter and energy governed by fixed physical laws. If the discovery points to the existence of forces or dimensions that transcend our current understanding, it raises questions about the limits of human knowledge and the role of consciousness in shaping reality. Some philosophers and physicists have already begun speculating about the potential connections between the CERN discovery and the nature of consciousness itself. Could the anomaly offer clues about the hard problem of consciousness? The question of how subjective experience arises from the interactions of neurons in the brain? While this line of inquiry is still highly speculative, it's possible that the discovery hints at deeper connections between the quantum realm and the human mind, offering new avenues for understanding the nature of thought, perception, and awareness. This discovery also reopens the debate on the idea of a multiverse, a concept that has fascinated scientists, philosophers, and the general public for years. The multiverse theory posits that our universe is just one of an infinite number of universes, each with its own physical laws and constants. While this idea has remained largely theoretical, the CERN anomaly could provide the first experimental evidence for the existence of parallel realities. If true, this would not only revolutionize our understanding of the cosmos but also force us to rethink fundamental questions about existence, causality, and free will. In the realm of cosmology, the discovery could offer new insights into the nature of dark matter and dark energy, two of the most profound mysteries in modern science. Dark matter, which makes up the majority of the universe's mass, has never been directly observed, but its presence is inferred from its gravitational effects on galaxies and other cosmic structures. Dark energy, on the other hand, is believed to be responsible for the accelerating expansion of the universe. The CERN discovery might offer new clues about the nature of these enigmatic substances, potentially leading to breakthroughs in our understanding of the universe's ultimate fate. Are we on the verge of discovering that dark matter and dark energy are manifestations of new forces or dimensions? If so, this would upend the standard cosmological model and lead to a complete rethinking of the universe's structure and evolution. The implications of the discovery also extend to the realm of theoretical physics, where researchers are already grappling with its potential impact on string theory and other attempts to unify the fundamental forces of nature. String theory, which posits that the universe's fundamental building blocks are not particles but tiny vibrating strings, has long been one of the leading candidates for a theory of everything. However, the theory has been difficult to test experimentally, and some physicists have criticized it for lacking empirical support. The CERN anomaly could provide new data that either supports or challenges string theory, offering clues about the true nature of the universe's most basic constituents. The discovery may also have implications for loop quantum gravity, another leading contender in the quest to reconcile quantum mechanics with general relativity. Loop quantum gravity suggests that space and time are quantized, existing in discrete chunks rather than as continuous fields. If the CERN anomaly hints at new properties of spacetime, it could offer insights into the validity of loop quantum gravity or point to a new, more comprehensive theory that bridges the gap between the quantum and cosmic realms. As scientists continue to explore the implications of this discovery, it's clear that we are standing at the precipice of a new era in physics. Just as the discovery of the Higgs boson in 2012 revolutionized our understanding of mass and the fundamental forces, this new anomaly promises to open up entirely new fields of research. It's likely that future generations of physicists will look back on this moment as a turning point in the history of science, a moment when humanity's understanding of the universe expanded in ways that were once thought impossible. In many ways, the discovery at CERN echoes the transformative discoveries of the past, from Isaac Newton's formulation of the laws of motion to Albert Einstein's theory of relativity. Each of these breakthroughs forced humanity to rethink its place in the cosmos and opened up new frontiers of knowledge and innovation. The CERN anomaly, while still in its early stages of investigation, has the potential to be just as transformative, offering new insights into the nature of reality and expanding the boundaries of human understanding. What's particularly exciting about this discovery is the sense of possibility it evokes. While the specifics of the anomaly remain shrouded in mystery, the mere fact that such a phenomenon exists opens up a world of new questions and possibilities. It's a reminder that science, at its core, is a journey of discovery, one that is never truly finished. With each new breakthrough, we are reminded of the vastness of the unknown and the excitement that comes from pushing the boundaries of what we know. As the implications of the CERN discovery continue to unfold, the scientific community is being drawn into new areas of inquiry that challenge even the most forward-thinking paradigms. The phenomenon observed has sparked a deeper examination into what constitutes the fundamental nature of the universe, prompting a broader exploration into topics that previously existed only at the periphery of mainstream physics. The sheer strangeness of this anomaly invites radical new ideas and forces the re-examination of long-held assumptions about space, time, and matter. One of the most immediate and profound challenges posed by the discovery is its impact on the notion of causality. Causality, the relationship between cause and effect, underpins much of classical and quantum physics. It's a principle that allows scientists to predict the behavior of particles, forces, and objects across time. However, if the CERN anomaly hints at forces or particles that transcend the known dimensions or interact with the fabric of spacetime in novel ways, it could fundamentally alter our understanding of cause and effect. The possibility exists that this discovery points to phenomena where traditional causal relationships break down or become nonlinear. This would challenge the very idea of determinism, the concept that the future is a direct consequence of the present, a principle that has long provided the foundation for scientific inquiry. Imagine a world where the familiar cause and effect chains are distorted or disrupted. In such a scenario, events at the quantum or cosmic level might not follow the predictable sequences we've come to expect. Particles could appear to influence one another across vast distances without any clear exchange of energy or information, possibly suggesting interactions across dimensions or outside of the temporal framework as we know it. If this is true, it would force scientists to rethink how they model physical systems, potentially leading to entirely new mathematical formulations to describe these non-causal relationships. This would also pose a philosophical challenge, as our conception of free will, determinism, and even the passage of time might need to be re-evaluated. If the discovery suggests that events are not bound by traditional causal structures, it might imply that time is more fluid or multidirectional than we currently understand. Some theoretical physicists have proposed that time may not be a fundamental property of the universe, but rather an emergent phenomenon, something that arises from deeper underlying processes that we are only beginning to glimpse through findings like this one. If time itself can be reinterpreted, the implications for everything from theoretical physics to metaphysics would be staggering. In the realm of cosmology, this discovery could push scientists to revisit and potentially revise the theory of the Big Bang. The current model suggests that the universe began as a singularity, a point of infinite density and energy, approximately 13.8 billion years ago, expanding rapidly in an event known as the Big Bang. This model has been successful in explaining many observed phenomena, such as the cosmic microwave background radiation and the distribution of galaxies. However, there are still unresolved questions about what happened before the Big Bang, whether there were events prior to this moment, and what physical conditions might have existed in those early moments. The CERN anomaly could offer new clues to these mysteries. If it turns out that the discovery relates to higher dimensional phenomena or new forces of nature, it might suggest that the Big Bang was not the beginning of time and space, but rather a transition between different states or dimensions of the universe. Some cosmologists have speculated that our universe could be part of a larger multiverse, where universes are constantly being born and destroyed, existing in cycles or through interactions with higher dimensional spaces. If the anomaly is indeed evidence of forces that exist outside our traditional understanding of spacetime, it could lend credence to these ideas and suggest that the universe is far more complex and dynamic than previously imagined. Additionally, this discovery could lead to a reconsideration of black holes and their role in the universe. Black holes, those mysterious regions of space where gravity is so strong that not even light can escape, have long fascinated physicists. They represent a breakdown of the known laws of physics, particularly at their singularity, where densities become infinite. Some scientists speculate that the CERN discovery might offer insights into how black holes function and what happens within them. It could even help to explain the long-standing mystery of what happens to information that falls into a black hole, a puzzle known as the information paradox. According to quantum mechanics, information cannot be destroyed, yet black holes seemingly erase all traces of the matter and energy that fall into them. If the anomaly at CERN points to unknown forces or dimensions, it could suggest that information is not lost in black holes, but rather transferred to another dimension or spacetime framework. Beyond black holes, the discovery might also affect how we understand the fabric of space itself. Physicists have long debated the nature of spacetime, with general relativity describing it as a smooth, continuous fabric that can be warped and bent by mass and energy. Quantum mechanics, on the other hand, suggests that at the smallest scales, spacetime is not smooth, but instead foamy and turbulent, with quantum fluctuations constantly roiling the fabric of the universe. This discrepancy between the two theories has been one of the central challenges in modern physics, and attempts to reconcile them through quantum gravity, string theory, or other approaches have yet to produce definitive results. The CERN anomaly could offer new insights into this divide, potentially revealing that spacetime is more complex and dynamic than either theory alone suggests. If the anomaly is a manifestation of interactions between spacetime and previously unknown forces or particles, it could point to new structures or behaviors in the fabric of the universe that we have not yet observed. This could lead to a deeper understanding of quantum gravity and help to bridge the gap between quantum mechanics and general relativity. It may even suggest that spacetime itself is emergent, arising from more fundamental processes that operate beyond our current conceptual frameworks. Such a revelation would not only affect our understanding of the universe's large-scale structure but could also have profound implications for quantum field theory, which describes how particles and forces interact at the smallest scales. If spacetime is not the immutable backdrop against which these interactions occur but is instead a dynamic entity influenced by unknown forces, it would necessitate a radical rethinking of the basic assumptions underlying quantum field theory. This could lead to new predictions about the behavior of particles and forces under extreme conditions, potentially opening up new experimental avenues for high-energy physics. One of the most exciting possibilities raised by this discovery is that it may lead to the identification of entirely new forces of nature. Until now, scientists have recognized four fundamental forces: gravity, electromagnetism, the weak nuclear force, and the strong nuclear force. These forces govern everything from the motion of planets to the behavior of atoms, and they are described by the standard model of particle physics and general relativity. However, the anomaly at CERN could suggest the existence of a fifth force, or even more forces, that operate in ways we have never observed before. This would be a groundbreaking development, as it could help to explain some of the unresolved mysteries of physics, such as the nature of dark matter and dark energy. Dark matter, which makes up most of the mass in the universe, does not interact with the electromagnetic force, making it invisible to traditional methods of detection. However, if there is a new force that affects dark matter, it could provide the key to finally detecting and studying this elusive substance. Similarly, dark energy, which is driving the accelerated expansion of the universe, might be influenced by unknown forces that operate on cosmological scales. If the CERN discovery points to new forces that interact with dark energy, it could offer insights into the ultimate fate of the universe and whether its expansion will continue indefinitely or reverse at some point in the future. The discovery might also challenge the very concept of mass and gravity. The Higgs boson, discovered at CERN in 2012, was instrumental in confirming the mechanism by which particles acquire mass. The Higgs field, which permeates all of space, interacts with particles to give them their mass. However, if the new discovery involves interactions between particles and forces that transcend the Higgs mechanism, it could suggest that there are additional unknown ways that mass is generated. This would be a profound shift in our understanding of particle physics and could lead to the identification of new particles that interact with mass and gravity in novel ways. If you liked this video, please give it a like and subscribe to our channel. Also, could you leave your comments below and tell us how this discovery could change everything? We want to hear from you. Thank you for watching and see you next time.